Okay, so in this lesson on section 4.3, we're going to learn a couple of different methods for solving systems of equations. And all the ones we're going to do today, we're going to work with a linear equation and a quadratic equation, which means we're going to have the graph of a line and a, what's a quadratic give us?
Parabola.
A parabola. Okay, so if you have a line and a parabola, you might get two intersections, like that, or you might get one intersection, like that, or you might get no intersection. Okay, so we're going to solve these two different ways. We're going to solve them algebraically, and we're going to solve them graphically. Now, in this section of the book, they are strictly doing lines and parabolas, but the methods that we're going to learn would also work if you had two parabolas, or if you had a circle and a line, or anything like that. These methods would still work for any combination of graphs if we want to find an intersection. And so let's start off with this first example A, and we're going to first solve it algebraically, and we can do that typically by using substitution. So looks like it would be pretty easy to get y by itself here. So if I take this equation and I want to write y equals, what would go on the other side of the equal sign?
3.
What do you think, Kyle? Y equals?
Negative 3x plus 7.
Let's see. So let's start with this.
3x minus.
Say that again.
3x minus.
Y equals 3x minus 7. That's correct. The way we get that, one way to get that would be to add y to both sides and subtract 7 from both sides. So if I add y to both sides, I have y, and then we are subtracting 7, so that's going to leave us with 3x minus 7. So that is correct. Y equals 3x minus 7. And once we have one of the variables by itself, then we can use that to substitute that expression in place of that variable in the other equation. So in place of that y, I'm going to write 3x minus 7. So this equation is going to become 3x minus 7 plus 4 equals 2 times x plus 5 squared. And so now if we expand this out, simplify as much as we can, so this is now 3x minus 3 equals 2 times, what's x plus 5 squared?
X squared plus 10.
Hopefully no one says x squared plus 25. Because when you multiply x plus 5 times itself, what do you really get? X plus 5 times x plus 5. That's x squared
Plus 10x.
plus 10x
Plus 25.
plus 25.
Yeah.
Okay, so now we have 3x minus 3 equals 2x squared plus 20x plus 50. And we can move everything to one side. 2x squared plus 17x plus 53. Okay, now let's think about the methods that we have learned for solving something like that. Okay, raise your hand if you remember one method that we could use. Jason?
We can use use the formula so we can use negative b plus or minus root b squared minus 4ac divided by 2a.
Okay, that's true. We could use that. What's that called when we use that formula? The quadratic formula. So we could solve this by the quadratic formula. What would be another method that we've learned? Patrick?
Completing the square.
Completing the square. Okay. Completing the square always works, but in this case, why would it be probably our last choice? Because of the 2 in front, and the other numbers there are odd. So we could use completing the square, but that certainly wouldn't be my first choice because of the 2 in the front. Okay? What's another method that we've learned for solving quadratics? Factoring. So my suggestion to you is that whenever you come across a quadratic equation, you try factoring, And if you try factoring for, let's say, a minute, and you haven't figured out how to factor it yet, then go to the quadratic formula. Because sometimes factoring can be pretty quick and easy, but if it starts taking a long time to factor it, so already we know that it's going to be 2x times x, and we just have to figure out, is there a way to write factors of 53 so that when I add up the middle terms, I get 17x. So go ahead and try that for a minute or two, and if you don't come up with a way to factor it fairly quickly, then go to the quadratic formula. So I'm going to pause this for a minute, and you go ahead and see if you can either factor it or solve it by the quadratic formula. Okay, is there anybody that was able to factor this?
Yeah. No.
No, it is not factorable because 53 is prime, so that means we're either going to have 53 times 1, like that, which would not work because then our middle term would have to be 55. Or, if we did it this way, 1 times 53, then our middle term would be 107, and that wouldn't work either. Okay? So it's not factorable. And so then if we go to the quadratic formula, we end up with x equals negative 17 plus and minus the square root of, what did you get for the discriminant, Panate?
3i.
What's the discriminant? What's the inside when you do b squared minus 4ac?
17 squared minus 4 times 2 times 53.
And what is that?
289 minus 424.
Which is negative 135. Okay? Over 2a, which is 4. Okay? Now since we have a negative under the radical, the discriminant is negative. That tells us there is no real solution. So that means our line and our parabola do not intersect. Okay? So no real solution, no intersection. Okay? So we solved it by the first method, which was algebraic. Okay? Now take out your graphing calculator and we'll do the same thing graphically. Now for both of these, to solve graphically, we need to have y by itself. So in the first one, we already got y by itself. Kyle told us that that was y equals 3x minus 7. Okay? And then in the second equation, all I have to do is move the 4 to the other side, and I have y equals 2 times x plus 5 squared minus 4. Okay? So those are the two equations that we want to type into our graphing calculator. So we're going to have y equals 3x minus 7, and y equals 2 times x plus 5 squared minus 4. And then we can always start with zoom 6 to get our standard viewing window. Zoom 6 gives us the 10 by 10 viewing window, and we can always adjust that if we can't see it, but we can definitely see here that the line and the parabola are never going to intersect. And so the graph is consistent with the algebraic answer that we got, which is that there is no solution. So it looks something like this. We have a line and a parabola that looks something like this. They never intersect, so there's no solution. Okay, any questions on example A? All right, and then if we go to example B, we're going to do the same two methods. We're going to solve it algebraically and graphically. To solve it algebraically, remember I used substitution the last time. We can use substitution again, but one thing that's going to be different is in the previous problem, we used we got y by itself in the linear equation because it was really easy to get y by itself. But in this one, it looks like we already have y by itself in the parabola. So I can just leave it like that. That's what I'm going to use to substitute in place of this y in the other equation. So it doesn't matter if you're substituting the linear into the parabola or the parabola into the linear. It will work either way. And so now I'm going to rewrite this equation, 3x minus 2 times y, but in place of y, what should I write?
1/4 x minus 3 squared.
1/4 x minus 3 squared. Good job, Sarah. And then that equals 13. Okay? And so now we want to expand and simplify. So we have 3x minus 2 times 1/4 is 1/2. So that's going to become 1/2. And then when we multiply x minus 3 times itself, we're going to get x squared.
I think you meant to write 1/2.
Oh, you're right, I did. I said 1/2 and then I wrote 1/4. Thank you. Okay? All right. So we have 1/2 of x squared minus 6x plus 9. And then it would be really nice if I didn't have that 1/2 there. So what do you think we could do?
You can multiply -2 on both sides.
We can multiply everything by 2. Multiply both sides by 2, so then that becomes 6x plus, or actually it's still minus, minus x squared plus 6x minus 9 equals 26. We have a negative in front. When I multiply 2 times 1/2, I would get 1, right? So here, let me do it in 2 steps to make sure that everyone's clear on this. So that becomes negative 1 times x squared minus 6x plus 9. So then when I distribute the negative 1, I have 6x minus x squared plus 6x minus 9 equals 26. And so move everything to the left side or move everything to the right side, and we would have 0 equals x squared minus 12x plus 35. And then remember again, we want to try to factor it. If we can't factor it, then we'll go to the quadratic formula. What is a factor pair for 35? 5 times 7 gives me 35. So if I do 5 and 7, is there any way I can get a negative 12 out of that?
Yes.
Yeah, if I make them both negative, then I have x minus 5 times x minus 7 will factor that correctly. And so my solutions are x equals 5 and x equals 7. And remember what we're trying to find. We're trying to find the intersection points of a line and a parabola. So the x coordinate is not all I need. I need the actual points where they intersect. So now we can go back to the original problem up here, the original parabola. If I plug in 5, what do I get for y? Plug in 5 for x. Y equals 1/4 of 2 squared, which is 1. 1/4 of 4 is 1. And then the other one, if I plug in 7, that's 1/4 of 7 minus 3 is 4 squared, so I get 4. So our 2 intersection points that we get algebraically are 5, 1 and 7, 4. Okay? Any questions? So both of these I solved by substitution. Yes?
How did you get negative 12x? Wouldn't it be 12x?
You moved everything.
I moved everything to the other side of the equation. So I have a 6x plus a 6x, that's 12x, but we moved everything to the right side of the equation. I did that, the reason why I moved everything to the right side is because I like a to be positive, and so I had a negative x squared when it was on the left, so I moved everything to the right. That's not the only way to do that. I could have left everything on the left side and then multiplied everything by -1, and that would have given us the same equation. Okay? Any other questions?
Can you plug it into both equations up there?
You can plug it into either one. I didn't have to plug into the parabola. I could have plugged 5 into this equation, and that would have given me 3 times 5 minus 2y equals 13, and then subtract 15 from both sides. That would have given me -2y equals -2, so y equals 1, so that gave me the same answer. Okay, so it doesn't matter which equation you plug into. The reason why I plugged it into the first one is because we already had y by itself, so then we already have y equals by doing it that way. Okay, now let's try the same problem on the graphing calculator. So the first equation is we already have y by itself. The second equation, I need to get y by itself. So that's going to be y equals -3x over 2, actually positive 3x over 2, minus 13 halves. Okay, talk in your groups to see if you agree with the second equation. How did I get that? And do you agree with it? And then if you do agree with it, go ahead and graph them both on your graphing calculator and see if you see the intersections.
It was 3x minus 2y equals 13. Because
Mr. Dixon,
Yeah.
when I graph, it goes into like a scatter plot type thing, kind of like this. I would like.
Okay, so I typed in these two equations and graphed it on the standard viewing window, and I do see that there's some intersections there. They're a little bit harder to see, so let me show you a trick that sometimes helps you zoom in a little bit to get the window exactly where you want it. And so just watch up here. You don't need to do this on your calculator right now. Just try to watch the steps. If I choose zoom box, that's the first option. What I'm going to do is I'm going to create a box around what I want my new window to be. So imagine a rectangle. I'm going to move the cursor to the upper left-hand corner of where I want my new rectangle to be. So I'm picturing a rectangle that has its upper left-hand corner right about there, and then I press enter, and then I move diagonally to the lower right-hand corner, and this rectangle will become my new viewing window. Okay? And then I press enter. And that's not a totally necessary step, but it just gives me a slightly better view. And so now to find the intersections, I'm going to go to second calc. And option 5 is intersect. Okay, we don't want to use trace or just moving the cursor around to find intersections. We want to find the intersections using the intersect menu. So it's asking, am I on the first curve? And it looks like it's on the blue parabola, so I'm going to enter and say yes. And then it says, am I on the second curve? Yes, I'm on the red line, so I press enter. And then guess means try to move the cursor close to the intersection that you're trying to find. So I'm trying to find this intersection right down here. And so when I press enter, it says that that point is at x equals 5, y equals 1. And notice that is exactly what we got over here when we did it algebraically. We got x equals 5, y equals 1. And now let's go through the steps again. For the second intersection, I'll go second calc. What am I looking for? An intersection, so that's option 5. And then first curve, enter, second curve, enter, and then guess. Now I'm gonna move the cursor until it's close to the other intersection. Okay, so that's probably close enough. Now enter. And it gives me that solution at 7, 4, which also matches the solution we got algebraically. So now for my solution, I'm just going to draw a quick sketch of what I saw. And I saw an intersection at 5, 1 and 7, 4, and a parabola that might have looked something like that. And so I had a line and the intersection at those 2 points, 5, 1 and 7, 4. Okay? Any questions on that example?
No. Nope.
So again, I want to emphasize that we do not use trace for finding intersections. We don't just move our cursor around to find intersections. We use the calc menu and the intersect feature. Okay? So now go ahead and work in groups on problems C and D. Notice that D is not a parabola and a line. What is it?
It's
What is x squared plus y squared equals 2025?
it's a circle.
It's a circle. Remember, x squared plus y squared equals r squared. So this time it's a circle, but the mathematics will be the same.
Was that Patrick?
Okay?
Patrick Francis. No way.
So pause it and then. So either substitution will work, but I did this one. I got x by itself in the top equation, and then substituted it right there in place of that x. And so when I multiplied all that out, then I ended up with this expression, which I can factor as y minus 6, y plus 3. And then when I solved that, I got y equals 6, y equals negative 3. And then to find x, we want to take those and plug them back into the original, into this right here. And so it says x equals negative 1/6 of y squared plus 6. So that would be negative 6 plus 6 is 0. And then for the other one, negative 1/6 of negative 3 squared plus 6. And let's see, what is that? So when we plug in negative 3, we get negative 1/6 of 9 plus 6. And that is 4.5 or 9 halves. Okay? So those are the two intersection points we get doing it algebraically. And then if you graph them, oh, I did show the other method here. If you did the other substitution, if you did the substitution the other way, and then doing it graphically, we get a sideways parabola. So in order to graph this on your calculator, this is a little bit different than the other ones because we have the y squared. So you have to get y by itself in order to graph it on the graphing calculator. So that's what I did here. I went through the steps to get the y by itself. So then we end up with, when we take the square root of both sides, remember we have to do plus and minus. And that gives us two different equations. So when you do the plus, that gives you the top half of the parabola. And when you do the minus, it gives you the bottom half of the parabola. And so that gives us the parabola and the line showing the same two intersection points that we got algebraically. So the key there is, in order to do it on your graphing calculator, you have to solve the equation, solve the parabola equation for y. And so that gives you these two half parabolas, because your calculator is a function plotter, and so we have to break this parabola into two different functions, because by itself it's not a function. It fails the vertical line test. And so we have to graph it as two different functions by doing the positive square root and the negative square root. Okay? All right. And then let's go ahead and try problem D. See if you can solve that one algebraically. Okay, so I took this equation and got y by itself, so y equals 1/20th x plus 15, and substituted that into this equation in place of this y. So now my first equation becomes x squared plus x over 20 plus 15 squared equals 2025. And so then we get x squared plus, let's see, if I do x over 20 plus 15 times itself, then that gives me x squared over 400 plus 15x over 20 plus another 15x over 20 gives me 30x over 20. And then 15 times 15 is 225. Okay, and then now I want to combine all like terms and move everything to one side. So these two terms are both x squared terms. So think of this first x squared as being 400 over 400. So that's 401 x squared over 400. And then 30 over 20 is 3 halves, so 3 halves x. And then minus, so if I subtract 20, 25 from both sides, that gives me negative 1800 equals 0. Now one thing you can do to make this a whole lot easier is get rid of all the fractions. So if I multiply everything by 400, I'll have no more fractions. And so then that's going to be 401x squared plus 600x minus 720,000 equals 0. Okay, so that doesn't look like it would be very fun to factor, so I'm going to go straight to the quadratic formula. So in this case, A is 401, B is 600, C is negative 720,000. So when I solved that, I got, using the quadratic formula, x equals negative 3 halves, or actually negative 600 using the second method, so that would be negative 600 plus and minus the square root of the discriminant ends up being this huge number 1155240000 divided by 802. Okay? Now if you plug all that into your calculator, if you do the positive, you end up getting, if you do the plus, because it's plus and minus, if you do the plus, you end up getting negative 43.13 approximately. And if you do the minus, you end up with, oh wait, actually that one is the minus. When you do the plus, you end up getting 41.63. So those are the two x coordinates that I get, negative 43.13 and some y value, and then 41.63 and some y value. Okay, and then we can go back to the original substitution that I did, which is here. If I plug those in for x, negative 43.13 divided by 20 plus 15 gives me about 12.84. And then if I do 41.63 divided by 20 plus 15, I get y is about 17.08. Okay, and then to solve this one on the graphing calculator, what we first need is y by itself. So in the line, we already had y by itself. Y was 1/20th x plus 15. But in the circle equation, if I move the x squared to the other side, I have y squared equals 2025 minus x squared, which then leads to y equals positive and negative square root of 2025 minus x squared. Okay, so those are the equations I'm going to graph. So if I put those in the calculator, the first one is 1/20th times x plus 15. And then the circle requires two equations. I'm going to have the square root of 2025 minus x squared, and then negative square root of 2025 minus x squared. So if I graph this on Zoom 6, I don't see anything. And that's because we need to think about where these lines are, or where the line and the circle are. The line has a y-intercept of 15 and a very shallow slope. So it's going to be way up here at 15 with a very shallow slope, actually sloping in the positive direction. So that's why we can't see it, because we're looking at a viewing window right here. Okay? The circle has its center at the origin, but what's its radius? Look at the equation of the circle. What's the radius?
45.
Yeah, the radius is 45 because the square root of 2025 is 45. So the circle is way too big for our current viewing window. So I'm going to change my viewing window so that I can see the circle. And so I'm going to go all the way out to 60. So negative 60, 60, negative 60, and 60. Now I should be able to see the circle and the line. There's the top half, there's the bottom half, and both intersections are on the top half, so I don't really need the bottom part of the circle at all. And now I can find the intersections by going to second calc, intersect, first curve, it's on the blue line, so I'll say enter. Now it's on the red top half of the circle, I'll press enter, and guess. So I'm going to move over to the left to get close to that intersection, and press enter, and it gives me the intersection at negative 43.13, 12.84. Notice that that matches the first one that we got algebraically. Okay? And then you could repeat that process to get the second solution. So that is second calc, intersect. First curve is the blue line, enter. Second curve is the red top half of the circle, enter. And then guess, I need to move way over to the other side. And I don't have to get right on it. As long as I'm closer to that one than I am to the other one, it'll find it for me. And so it finds it at 41.63 17.08, and that matches that solution as well. All right, so that completes the notes on section 4.3. So you need to know how to solve these systems algebraically as well as graphically on your graphing calculator.